we'll now move on to some of the technology underlying blockchains that allows them to actually function. We'll start off with hash functions. Now, if you ask a mathematician what a function is, they tell you it's a mapping between a range and a domain, which you can think of as you have a bag of objects and you have strings connecting them to objects in another bag. When computer scientists talk about functions, they mean a self-contained procedure code that returns an output, usually given an input. And the difference between a function and procedure is that a procedure doesn't have to have an output. But a hash function is a computer function that allows you to map some data, regardless of how small or big it is, to a snippet of data with a fixed size. And the values that a hash function returns are called hash values, codes, sums, or just hashes. And I'll just call them hashes because it's shorter. So popular hash functions, there's RIPEMD 160 returns 160 bits. SHA-5112 returns 512. One I was playing around with a few weeks ago is Blake. There's 256-bit hashes. And for blockchains, we want these hash functions to have some very specific properties. We want them to be deterministic, so you don't want the output to change over time. The really important one is collision-proof. If you have different data, you want the hash function to return a different output for those two different lots of data. You don't want different inputs to give the same output. And finally, for blockchains, you want the output to be unpredictable. You don't want to be able to manipulate your data slightly in order to get exactly the output you want. They've got to be a kind of pseudo-random number generator, in a way. So if I go over here, there's a link to an online hash calculator for SHA-256, which returns 256-bit output. If you put in hello, world, ! You get this number, which I've written in hex out. If you change it to hello world with a lowercase h, you get a totally different string. And if you drop the punctuation, you get yet another string. And that's really important. It's really bad if you pick a hash function that regularly returns the same hash value for different data inputs. So now I'm going to move on to this proof of work that I was talking about before. So it's based on an algorithm called Hashcash, which was invented by Adam Back in 1997. And his suggestion was that for a proof of work, and it was initially proposed to prevent spam in emails. So the idea was that you would take your data, which in this case would be an email, and you add a small amount of extra data, which is called a nonce. And then you hash it twice. So you hash it once, so your email plus the nonce hashed gives you this 256-bit number, and then you hash that number. And the SHA-256 algorithm takes a bit of computational power, so it takes time. And then you look at your resulting output. And remember, the output is just a number. So then you say, right, it's only valid if my output is smaller than a given value. That's a target or a difficulty. So if you set that very low, chances are, like if we go back here, you're going to get a fairly big number. If you set that number very low, you're going to have to try this proof of work algorithm again and again and again. But because you're changing the nonce each time, you get a different output. And eventually, hopefully, you'll find a value that is smaller than your target, and that's a success. And the idea with the spam fighting was that you would only accept emails that had gone through this process maybe 10,000, 100,000 times before the person found a number that was small enough. They send you the email. Your email server would check, and it would reject it if the hash output of the email was bigger than the difficulty. And that would stop spammers, because they would have to do this for every single email they were sending to every single person they were spamming. And it would just be too much computer power. But it never really took off. And as a result, our inboxes are still full of spam. We've gone with spam filters instead. For example, let's see if we can find a nonce to add to hello world that gives a SHA hash starting with a 0. And I actually had a little program here, some practical stuff. Up. So hello world 1, 2, 3 doesn't do it, 4 doesn't do it. This keeps running along. I put a 1 second delay in, by the way, because my computer's not that slow. But there we go, 17, 18, and 19. There we go. So it took 19 goes to find a hash starting with a 0, which would make that a smaller number than all the other numbers we've had. So there we go. That was a proof of work. I proved that I had 19 goes at finding a hello world message that had a hash starting with a 0. And you can look at the probability of how long you expect it to take. You expect it to take about 16 goes. So if you wanted a hash input starting with 3 zeros, you can work out what's the probability of succeeding there. And the answer is 1 in 4096. So you can see as you look for more zeros in front, the chance of finding a hash of the input starting with that many zeros is going to be 16 to the power of k goes. But, and this is the key thing, it only takes 1 go to check whether something that someone gives you actually has that many zeros at the front. So in summary, finding a block is hard, but checking that a block is valid is easy. And we want it to be like that. We don't want the work for checking to be laborious, otherwise we're not going to bother. So the next thing with proof of work is this dynamic adjustment of difficulty. So if more peers or more miners join, they're going to find a block more quickly because you're going to be doing more of these hashes in the same period of time. And similarly, if some of the peers leave, then it might take longer to find a block. And so what happens is the system has a target called a difficulty, and you adjust it every n blocks to keep the expected time to generate the blocks about the same. For Bitcoin, n is 2016. Every 2016 blocks, the system looks back over those blocks, looks at how long it took to find them, and then the difficulty is calculated accordingly. And this is a deterministic algorithm. You can go and look at the blockchain, and you can just compute what the difficulty should be given the previous history. There's no sort of discussion or arbitration here. There's a formula that says plug in the time it took to create 2016 blocks, look at the difficulty for the last block, adjust the next difficulty for the next 2016 blocks to be this value. And so that's how everybody working on the blockchain can agree to it. It's just there in the maths. And then I had a graph of the probability of finding a block in a given time. It's a geometric distribution. If you look at a cumulative one for finding a leading 0, you can see that initially finding on your first go is fairly low, it's below 0.1, but finding it in at most 16 goes is over 0.6, and it heads off towards 1 eventually. There's one other thing I want to discuss. Maybe I've gone past it already. No, it's okay. So one thing to realize here is that it's a probability of finding a block. On average, you're going to find a block in 10 minutes, but it could take you a second if you're really lucky. If you're really unlucky, it could take you a couple of hours. But on average, over time, it's going to take 10 minutes. Now, this is a problem because if you wanted to buy a cup of coffee with a cryptocurrency and you happen to buy it at the point that it takes 2 hours to find the next block, then the shopkeeper and you are going to get rather bored waiting around for that confirmation to happen. But on the other hand, if you're buying a cup of coffee, the shop owner is probably not going to be too worried about occasionally not getting his payment. But yes, if you're buying a house, then you probably would want to wait a long time to really make sure that it's been confirmed in the blockchain. So the question is, why are we doing all this work? Because finding these blocks means you've got computers running, and when computers run, they make heat, and that heats up the planet. And, it costs money. And the reason is it solves a problem known as the Byzantine generals problem. Provided over half the computing power on a blockchain network is good, the evil part probably won't be able to subvert the system for long. The smaller the evil part, the less likely they are. There is still a probability that they could, but it drops off very, very rapidly. So it's a way for a distributed system to reach a consensus and to stop a small minority from messing it up for the rest. But as I referred to earlier, there are some other less power-intensive solutions being investigated. They're called proof of stake. There's this proof of elapsed time, and there was this paper in the late 90s published about practical Byzantine fault toleration, which IBM is now folded into their blockchain. So I think it's worth discussing this Byzantine generals problem. I don't know why, but computer scientists seem to like having these kind of archaic problems. I remember from my undergraduate days the dining philosophers problem for stopping deadlock, where they had Greek philosophers with not enough cutlery to get by feeding themselves. And for some reason they picked the Byzantine Empire to base this problem on. And Nakamoto summarized it actually in quite a neat way that illustrates it in better than the traditional problem for blockchains. He said you've got a bunch of these generals, and they've each got a computer, and they want to attack the king's Wi-Fi by brute forcing the password. And they know it's a certain size, so they know that they can crack it through a brute force in a certain amount of time, given a certain amount of computer power. And they also know that once they start the attack, they've only got a limited amount of time to hack in and hide that they've done this. Otherwise, they'll get discovered, and it being something going on 1,500 years ago, they get executed. So they only have enough CPU power to crack it fast enough if the majority of them attack at the same time. So that's the problem. How are they going to coordinate their attack? They don't care when the attack is going to take place. They just all, or the majority, need to agree on it. And you don't want a minority attacking early, because that minority will get executed, and the opportunity to hack into the king's Wi-Fi will be gone, because he'll tighten up security. So the generals have decided that anybody can announce an attack time, and whatever time is heard first will be the official time to attack. But the problem is that the network is not instantaneous. So if two generals announce a different time at close to the same time, some of the generals are going to hear one attack time and some are going to hear the other attack time, and if that happens, they're in trouble. So that's the problem. Here's a Byzantine general. And how are they going to coordinate their attack time? So they need to reach what's called a consensus. And Nakamoto proposed this proof of work chain to solve the problem. Once a general receives an proposed attack time, he sets his computer to work on a proof of work problem that includes that attack time in the block of data to hash. And every time, and we were talking about generating these blocks and setting a difficulty so that you can't instantaneously make one. So every time a general creates a block, they announce it on the network, and all the generals that were working on the blockchain switch to generating the next block. And if there are two competing blocks, because two times have been announced, then some of the generals will be working on one fork of the block and chain, and some will be working on the other. However, at a certain point, one branch of the fork will be longer than the other, and everybody will see that and go, "Oh, I'll work on that one instead." And I've got some diagrams to illustrate that. Here we go. Two generals on the left there announcing attacking at 2 o'clock and at 3 o'clock tomorrow. And it turns out that 3 of the generals get the top block first, and 2 of the generals get the lower block first. And they start working away on this proof of work. And because there's 3 guys working on the top block, probability is that they'll find a second block sooner. You see there's a time axis along the bottom. But the 2 generals at the bottom find the block 2. But the 3 generals at the block have now found a third block. And at this point, because this is all being broadcast on the network, the 2 generals who are working on the slower chain go, "We're going to switch to working on the longer chain." And in this way, they've actually reached consensus. Now all of them are working on the same piece of data. They've managed to agree that 2 o'clock is the time to attack. And they keep working. Eventually you have a number of blocks, maybe 8 blocks, and you can actually compute how much CPU power was used to create those blocks. And if that amount of CPU power is the same amount that you need to brute force the Wi-Fi, then you're done. You can stop working on the blockchain and start cracking the king's network. So that's how Nakamoto explained the proof-of-work system. And it's been functioning on Bitcoin for the last 8 years now, 7 years. Yeah. So then another thing you need to have on the blockchain is that you need to have the concept of identity. So you need to know who's participating, who is submitting what, or who owns what, or who does what. In the case of logging inventions, who invented it. Or in the HR one, who worked where and for how long. So identity becomes important. And this is not identity in terms of your passport, which says, you know, I'm Keir Finlow Bates. It's just knowing that it's the same person doing things. There are some people in the press saying that, oh, Bitcoin's anonymous. It's not truly anonymous because you can track the activity of a particular entity on that blockchain. It's just hard to know who that person is in real life. But eventually you could actually work it out. There's a whole forensic departments in the FBI who use sort of techniques to track down people who've done bad things using Bitcoin. So, anyway. And the way that's used at the moment is asymmetric key cryptography. It's also known as public key cryptography. And you have a public key, which is your public identity or your face on the network. And nobody can pretend to be you because only you have the private key associated with the public key, which is kind of like your soul, your sort of true identity. And you keep your private key secret, and it's really important to do that. And if I have time later, I'll be showing you why. And a simple summary of asymmetric key cryptography is that you create a private key, you use that to create a public key, and then there are 2 very simple things. Anything encrypted with the private key can only be decrypted with the public key. So here we have hello world turned into this gobbledygook, and then the only way to get the gobbledygook back to hello world is with the public key. And anything encrypted with the public key can only be decrypted with the private key. So at the bottom, hello world, encrypted with the public key, gives you a different ciphertext, and it can only be decrypted with the private key. And because you use the private key to generate the public key, it's not fully symmetric. Well, this is basically it. That's kind of, in a nutshell, how it works. And then there's some maths. I'm not going to go into too much depth. There's probably people here who know a lot more about it than me. But basically, we're talking about how it works. Now, the engine underneath it is based on this idea of one-way functions. Functions where it's very easy to do a calculation in one direction, but really hard to do it in the other direction. And the simplest one to sort of get your head around is factorization versus multiplication. It's really hard to factorize 1,643 in your head. Most people can't do it. Some people would have difficulty doing it with pen and paper, and even if you have pen and paper, it will take you quite some time. However, most people can do 31 times 53 on paper, and some people can even do it in their head. As it happens, 31 times 53 is 1,643, so the second line is the factors of the first. So here you have a function where doing it's easy, undoing it is hard. And that is sort of, roughly speaking, how RSA, one asymmetric key cryptography system, works. Other popular ones, there's a system called El-Gamal, which relies on something called discrete exponential and logarithm, that it's easy to take exponentials, it's hard to do logarithms. Have I got that the right way around? I think so. Another one is modular squaring. So modular arithmetic is the clock face arithmetic, where if you add numbers and they get above the mod number, it resets back to 0. And it turns out that if you take a modular arithmetic where the modulus is a product of 2 primes and you start squaring numbers, it's really hard to do the squaring if you don't know the prime numbers, but there's a trick for doing it very easily if you do know the prime factors of the modulus. And one that we're going to look at a bit more detail is elliptic curves. You have elliptic curves specified by that equation. Y squared is x cubed plus ax plus b. When you go online, all the diagrams show these as continuous curves on the reals, but actually for cryptography you do it over a discrete finite field. And it turns out that there's this, the elliptic curve defines a bunch of integer points in that finite field, and if you multiply, there's a way of definition of multiplication of a constant by a point that gives you a new point. And it turns out that if you know k and r, you can work out p, or if you know k and p, you can work out r. But if you only know r and p, it's very, very hard to work out k. Someone explained this to me once in terms of if you look at imagine walking into a snooker hall or looking at a snooker table, and you're told that somebody put a ball on the table here and hit it at this angle, and it bounced off the edges round and round and round. It's a frictionless snooker table. And eventually they stopped the ball, and you can now see where the ball stopped. It's really hard to work out how many times it bounced off the edges of the billiard table, other than recreating the whole experiment. But if you have some extra data, then it's trivial to do. So these are the kind of functions that asymmetric key cryptography relies on. And I'm not really the person to sit here and talk for an hour on it. It's better to go off if you're interested and find there's some very good tutorials on the web. But you don't actually need to understand the maths. All you need to know is this idea of a public-private key, and that there are some libraries out there which implement these key schemes. OpenSSL is one out there. There's packages for Ruby and Node.js. One thing you must never do is implement your own version of this for a production environment, because it's really hard. You think you've got it working, and then there'll be some subtle bug you've made, and other guys have made all these mistakes before you even fixed them over the last 20, 30 years, so rely on their work. I was using this Blake hash function, and it turned out that the Ruby package for it was actually an undergraduate student's project, and it worked fine for inputs less than 1,024 bits, and then failed miserably above that because he hadn't tested it. And so I would go with OpenSSL, because you don't really know the kind of history behind some of the packages of the other programming languages. I imagine Python, you're probably okay. So if you're going to do this stuff, it's also a good idea to kind of deal with these large numbers, how they're represented in different bases. Then you just start picking random private keys and using the functions to create public keys and start encrypting stuff. With a caveat, you really need to pick your private key randomly. And we'll probably get onto that in a bit. So the thing about these keys is you can use them to sign something. There's a very neat, simple algorithm that I thought would be worth talking about here, because it can be explained. Using your private key to sign something. So we've got this example here. We have Alice and Bob. In cryptography, it's always Alice and Bob. They've been a long-standing couple. Alice wants to pay $100 to Bob. So she wants to authorize this check, pay $100 to Bob's public key. And she does this in the following way. She takes a hash of the message, she encrypts the hash using her private key, and she attaches the hash and her public key to the message, and she sends that whole package onto the network. And in a blockchain, it'll be a peer-to-peer network. Right. And are the peers going to include this transaction in their next block? And, well, it's yes, on two conditions. Alice has to have $100 to transfer in the first place, and the signature has to check out. And the signature checking, well, they take the first half of the message and they recreate the hash. They take the encrypted message, they use her public key to decrypt it, and if there's two match, then the signature checks out. It was indeed Alice's private key that signed the initial request, and the transaction will be included. How do we know Alice had $100? Well, it turns out that in block 412 she got it from Carlos. So the other thing would be to check back on the blockchain to see that she actually had the money to spend in the first place. And we can go back and discuss later about where Carlos got the money from. Okay, so that's kind of covering how cryptographic keys are used to provide for identity and ownership on a blockchain. Now I'm going to touch briefly on scripts and smart contracts. So it's mainly because Nakamoto decided that he was going to handle these Bitcoin transactions using scripts. He could have just used a ledger system. He could have just said, right, you have a message that says this address owns this number of Bitcoins, and then later on say, this address authorizes sending this Bitcoins to this address. Instead, he used the scripting language and this kind of idea of flows of inputs and outputs. And he used this, well, it's described as a Forth-like. It looks quite like assembly to me. And it's a state machine with a stack to code coin transactions. Another blockchain I talked about, Ethereum, it uses this JavaScript-like language for coding contracts. The language is called Solidity. And it has these objects called contracts, but they're actually very much like classes. Fabric, which is IBM's contribution to the Hyperledger project, uses Golang. Go is a C-like language, and it's compiled into something called chain code that allows you to write little programs to run on a blockchain. And Sawtooth Lake doesn't use code as such. It uses these data structures and these SQL-like commands, and then the code, they've actually written the code for you in Sawtooth Lake itself, and this is called Marketplace. They've kind of tried to abstract it back one layer so that you don't have to be a programmer to generate smart contracts. So smart contracts, well, they were proposed in 1994 by a guy called Nick Szabo. I think that's how it's pronounced. And it's just this abstract idea that you could use a computer program to execute a contract that's been agreed on. And blockchains sort of provide the opportunity to have a scripting language for the automated execution and this way of recording permanently that the contract is there. So you kind of got the permanence of a contract and the execution through the scripting language. And a related concept is this Ricardian contracts, which is from Ian Grigg in 1996. They are a design pattern that is meant to capture the concept of the contract before you code it up. So with the two of them, you actually basically have this opportunity to take a contract that human beings understand, produce some machine-readable code so that they agree that it's going to do what they want it to do, and then code it up and execute it on a blockchain. Again, there's heaps of more on this stuff on the web if you want to read up about it. So I was going to look at a transaction script for Bitcoin. You have an input, which is a previous transaction that gives you money that you're allowed to spend. You have a signature, which proves that you are the person allowed to spend that, and then you have an output, how much you're going to spend and where you're going to send it to, which is where you're going to send it to is that where it says after op hash 160, that string of digits. And there's a script at the bottom there that actually will do some stuff. It's actually it gets executed in a Bitcoin peer. So Bitcoin basically contains a stack-based language, and there are commands to push items onto a stack, pop them off, do comparisons, do some cryptographic actions and stuff like that. and you build small programs. So the idea was to have some flexibility in the transactions. So it wouldn't just be about transferring value from one address to another. It allows you to implement the opportunity for requiring multiple signatures, or needing a certain amount of time to have passed before you can redeem the coins, stuff like that. And so it gives it flexibility, and I think that's what the inventor of Ethereum picked up on, this guy called Buterin, and extended it. And now it's kind of seen as one of the really valuable use cases for blockchains, that you can have these much more complicated programs running on them. I just thought I'd list some of the scripting commands. Here are a whole load of stack commands. So you can see you can manipulate items on the stack up and down at will. There's some simple arithmetic and logic options. And you can go and look up on the bitcoin.org site. They have the full list of commands available. There's a whole bunch of cryptographic functions as well that you can use. But it basically gives you the opportunity, and you can write a script up to 10K in length, and or rather, an output script up to 10K in length, and the whole size, technically you could have it almost 1 megabyte long. So you could write really quite a long program. The thing is, it's a state machine with a stack. It's not Turing complete. It doesn't have loops. So that does give you some limitations, but you can still do a fair amount. So Ethereum. So it was invented by Vitalik Buterin in 2013. He was 19. So that makes sense. Developed with some crowdfunding in 2014 and launched in 2015. And so that's quite a rapid turnaround, and it's quite a remarkable achievement. And it's a public blockchain, has an associated cryptocurrency called Ether, and it has this scripting language called Solidity, which looks like JavaScript and allows you to do a lot more stuff than Bitcoin scripting. If you want to run, if you want peers to run your program, you have to pay using the cryptocurrency associated with Ethereum. When you use your cryptocurrency like this, it's called gas. So give this sort of concept of fuel. You know, you use your Ethereum to buy fuel to run your program. If the fuel runs out, they're not going to run your program anymore. And it kind of is how the system pays for itself. And you can actually set a limit to make sure that it doesn't spend all your money. And when you go to the tutorials, one of the first things they tell you to do is make sure that your script has some kind of method for killing it, because otherwise you put it on there, it's there forever. It has to be compiled before it's submitted to the blockchain, because you've got to keep these blocks as small as possible. There are a whole bunch of different tools out there at the moment, and they seem to be creating more every month. The wallet for the cryptocurrency can be changed into a browser, and you can actually build and deploy contracts, scripts using that. If you install a Ethereum peer, one of these miners, on your machine, you get a command line interface called Geth, and it actually has a built-in compiler, so you can write your scripts in a text editor and then compile them with the command line and deploy them onto the network. There's a web browser IDE that you can write code in and compile it and then copy-paste it across. But then you need to have a wallet or a command line interface to deploy it. And there's this there's a number of different developers. There's a thing called Dapple, which allows you to write some code and test it before you deploy it. And there's some Node.js packages as well that give you a development harness. It fits quite neatly in there because Node.js is in JavaScript, and the two look quite similar. So a whole bunch of tools out there. If you want to play with it, you can fire them up, and a whole bunch of tutorials. I don't think it's worth me going into more depth here. And the thing about this is a public blockchain. Anybody can download the software, use it. You can check out the code from GitHub and tweak it for your own purposes. And there's quite a large community behind it. There's kind of big developer conferences going on all the time. So the other big thing is something called Hyperledger. And this is the blockchain project that the big companies seem to be supporting at the moment. It got handed over to the Linux Foundation about half a year ago, and the two big projects on it are Fabric, which is IBM's blockchain, and Sawtooth Lake, which is Intel's blockchain. IBM, I think, has put Fabric on there because it integrates with their IoT stuff called Watson, and Intel, I think, put Sawtooth Lake on because it's meant to be run on their trusted execution environment chip. So, of course, their businesses, they are going to want to use this technology to advance their business, and they see this as a way. But they're two totally different systems. You know, when someone talks about Hyperledger, that doesn't actually tell you what's being used. You need to say which one. So Fabric, there's a tutorial on how to set it up on the Chainfrog site. I spent an evening getting it up and running. I actually had to buy a new laptop because my old one didn't support virtualization well enough to run it. If you want to be a developer, you need to have a virtual machine. It runs this software, virtual box. Then there's a tool called Vagrant, which is a way of deploying a specific image so that all the developers are using the same development environment. It's an Ubuntu configuration. Then you can check out the code and fire up a peer and start it running. And it works. Of course, you'd expect it to. And you can go through the tutorials on the Hyperledger site. Actually try setting up your own blockchain and creating participants and transferring things between one another participant. If you want to deploy it, at the moment they use Docker, which is a containerization platform. It's a way of packaging everything up so you have all the required libraries and running it on whatever native platform you want to. And there's a Node.js package that gives you access to an SDK that allows you to then interact with the Fabric software. Right. A Sawtooth Lake also uses a virtual machine and Vagrant to emulate this trusted execution environment that normally requires an Intel chip for you to run stuff. So at the moment, from what I understand, you couldn't actually deploy a Sawtooth Lake system in a production way. You'd have to go with the Intel chip. And there's a really good tutorial on how to get up and running and working at that site. I'll be putting all these slides on Chainfrog's site later, so you'll be able to go there and download them, which walks you through. And as I said, they've abstracted away the scripting stuff, so they actually do most of the coding for you, and you just create these JSON-like data structures that you submit to it. And then there are kind of different models, like a voting system or a currency system or an authorization system. So in that sense, you're kind of limited in what you can do with it. But you can, of course, check out the source code and add your own system if you really want to spend the time getting to grips with the in-depth code.